Today's video will be about the ambiguous case of side-side angle. You may have referenced this back in geometry class, where if I have a given situation where they give me the angle, a side, and then the other side, some interesting things can happen with how many triangles are actually made. If we look at it through a program called GeoGebra, it does a great job of animating what the possibilities are and how many triangles come from those side lengths. So I'm given that the angle A is 30 degrees, side little b is 9, but then side A is just 3. If you notice with this given situation, it does not make a triangle. It would just dangle as we move it back and forth. As I increase that length, obviously then I'm going to be able to get to that third side and I'll be able to make a triangle. But specifically, if I hit this length of 4.5, it makes a right triangle. We're going to reference this as the height of that possible triangle. So if we notice that the length of A is shorter than the height, it didn't make a triangle. If the A is equal to the height, it made this one specific triangle. What we're going to see that's interesting is when it gets a little bit longer. If I increase this length of that second side, it's longer than the height, but it's less than that B value. What actually happens is we can get two separate triangles that have the given information of the angle of 30, a B of 9, and an A of 5.6, or something that's less than that height. So we'll talk about how many triangles we can get for given situations. It may be beneficial to take some notes on what A, B, and angle have to be to see when I get 0, 1, or 2 different triangles. The first situation we saw was when we have this length of H, that we would always call this height here, is longer than the value of A. Now, we can find the height of this triangle very easily by using a sine ratio. We can always draw this perpendicular, and the sine of A would be H over B. To solve for H would equal B sine of A. So we'll use that in the reference as we go when it gets a longer length for that. One of the ways we can get one triangle that we saw was if that A, that second side, across from my angle is exactly equal to the height. So if I know that second side is B sine of A, I would get one distinct right triangle. So again, to get no triangle, the A is less than H, which is less than B. If A is equal to H, but still less than B, we would get one triangle. Another way we can get one triangle is if the A is actually much longer than the B value. You can see if I rotated this around, it wouldn't hit the side AB again. It would just kind of rotate around here and it wouldn't make another triangle. So we can say that if A is greater than or equal to B, that will have one triangle. If it was equal to B, then we'd get an isosceles triangle. But this is just too long that it's not going to hit on the side AB anywhere else. The last situation is the interesting one for today. We can actually get two triangles if this A value is bigger than H, but less than B. As you can see in our picture here, if this was rotating around, this length A would hit over here, and it would hit over here, making two different triangles that we would have an obtuse triangle in this little guy here, and then a big triangle in ACB2. Our goal from here is, given certain angles and side lengths, to see is how many triangles we have. And when we do have multiple triangles, how can we actually solve all the sides and angles for both of those triangles? Here's a quick representation of what I showed before, that if I use this compass, this length is 40. So I have my 38, I have my 52 side B, but I don't know where angle B is yet, and that this side is 40. If I draw this out this way, it would hit right here. So this would be B. Or I could draw it this way. I'll just use the blue from there. Move this around. And I can use red then to say, okay, 40 could go this way as well. It would hit there. So if I get rid of my compass, we can have some side lengths to connect those two. So the blue would go out to here and create a triangle, ACB. And maybe I'll call that B2. Or I could have the red rotate here. Oops. Right to about there. And both of these lengths would be 40 to create two different triangles. Now from there we want to see, well, how does that change the angles? It looks like I have an obtuse angle here. It looks like I have an acute angle there. Maybe they have a relationship and we can solve for the sides and angles. I did also want to note that I did find the height right here just to verify that my length of 40 was longer than my height but less than 52. So we can solve this using the law of sines or the law of cosines. I'm going to show you first with the law of sines. Now here's my two possibilities, and what I'm going to do first is use the law of sines to get the first angle. Now I still don't know what picture I'm dealing with, but I'm going to have the same setup with the law of sines. It would look like this. So going through the law of sines, I set it up to sine of 38 over 40 equals a sine of b over 52, which would be the same in the red. But I notice when I solve for b sub 2, correct that here, I get 52 sine 38 divided by 40 equals the sine. So to undo that, I'm going to have to take the inverse sine of both sides. So b sub 2 is the inverse sine of that ratio, that quantity there, which is approximately 53.164. So if I'm looking at my two possible triangles, this one has an obtuse angle at B, this one has the acute angle at B. I'm going to say this one is the 53.164. Now I'm going to leave it up to you to find the remaining parts of this blue triangle. Notice that we have two angles. The angle that was given to us by our calculator. We can find the third from subtracting these two from 180. From there, I can set up the law of sines to find this longer side. But how are we going to attack this red triangle? There's two ways to think about it. I just took the inverse sine in my calculator. If we remember from our earlier chapters, thinking about the domain of inverse sine, we said that inverse sine in our calculator is only going to give us an answer from negative pi over 2 to pi over 2. So that's why it gave me this approximately 53.164. We know that actually there's another angle that has a sine value of whatever this number is that's over in the second quadrant. These two have the same y value. Now notice that green angle then is an obtuse angle that has the same sign. So I could take 180 and subtract 53.164, and that would be this red angle. Another way to think about it, which I think is pretty nice, is that I drew the extra red triangle here that I know this shape is an isosceles triangle. If that's the case, this angle, this base angle is equal to this base angle. So really, if I'm just looking for that red angle, to find the second angle, all you have to do, the second angle, is take 180 minus your calculator angle. So in my case, if I take 180 minus 53.164, I would get 126.836 degrees. And again, I may not show the remaining parts of how to solve or find the remaining sides and angles, just because we've been doing a lot of that in the last couple of days. But I have two angles. I can find the third. I can set up a law of sines to find that second side. So notice that we have two different triangles here. We have an obtuse triangle that would have a shorter length of AB, and then we have an acute triangle. This may be an obtuse angle, sorry, but our B value, our B angle is acute, that this would have a much longer side for AB. We can actually use this or solve using the law of cosines as well. So as you can see here, I set up these side lengths that I knew and kept that C variable. Now, as much as this may not look like it, think about what type of equation this is. This actually ends up being a quadratic. Notice that I have a C squared term. I have a kind of a weird coefficient with C, but then I have some constants. So let's put it equal to 0 and put it in that quadratic form. And that would look like this. I subtracted my 40 squared, eventually got 1140. This whole, I took the 2 times the 52, which is 104, then a cosine of 38, and then had that be my coefficient of C. And then really what I have now is my A, B, and C. I know I got a lot of variables, but A, B, and C in terms of the quadratic formula. So let's plug that in there, and I'm going to show you a little trick with your calculator. But I want to show you the store feature on your calculator. So this 104 cosine of 38, I use quite a bit, and you can use it a lot for doing some computations. So you can actually store certain variables and numbers to your variables. So like if I put in this 104 cosine of 38, I notice I'm going to use that a lot. So what I can do is press store, which is STO here, and I'm going to store it for a variable a, which I'm going to press alpha and then a. So as I press enter here, it's going to store it in that letter where I can use a anywhere then. So for example, let's say I want to find out what's underneath this square root. I can go alpha a, alpha a squared, and then I don't have to worry about closing parentheses, things like that, minus 4 times 1140. Don't need to do the times 1. Ends up saying that's 2156. So what I can do then is square root that. Now I'll have the decimal for that right piece there. This right here is 46.436-ish. Now if I want to find each of those x's, I'm going to go x equals. Now in my calculator, I can just put a plus whatever that decimal is and then divide by 2. So my plus answer is going to be a plus my answer above here, which I'm just going to go second answer. I'm going to press enter just so I don't divide my answer by 2. Answer divided by 2. And it says that side is 64.197. But we know with the quadratic formula, we actually get a second answer. So I can go alpha a, and then I'm going to subtract that decimal that I had after the square root. Which looks like this one. I'm going to press enter and then divide by 2. And look at that, 17.758. And with the work, hopefully, that you would look at solving this one the same, you get the same lengths. It works out both ways. Now you see the law of cosines, it's about the same amount of work. But what happens with the law of cosines if you go through this, you set up the picture and you get one answer? Guess what? There's one triangle. If you get one positive and one negative, that means there was only one length to begin with. So the law of cosines can really help you see if there is just 0, 1, or 2 triangles as well. If you're in class, we'll have a class cake to help practice with some of these, finding 0, 1, and 2, and finding the missing sides. If this is just extra help for you, hopefully that helped out.